This is an auto-ranging multimeter, and this is an old analog manual multimeter. When you measure with this multimeter, you need to know where you put the switch to not damage the multimeter.
We have here two manual ranging multimeters. This guy here is an analog one. Manual ranging means that you have to select manually the range in which you should measure. This one is a digital one, but also a manual ranging. This third one is a digital multimeter, but also an auto ranging multimeter. That means you only have to select what you want to measure, and from then on the multimeter decides what range we'll use. In case of an analog multimeter, when we measure DC voltage in the right polarity, this happens. If we accidentally switch the probes and measure in reverse bias, this happens. Yeah? In case of a digital multimeter, if we measure in the right direction, the multimeter displays 9.7 and some change DC voltage. Yeah? If we measure backwards, it displays simply a negative potential. It displays negative 9.7 volts DC. Let's measure some resistors. We simply put the multimeter in the resistance mode, and then touching the leads, we find out that this first one is 22 ohms, the second one is 1K. We're talking standard values. This third one is obviously 8.2, because that's a standard value, 8.2K. The third one, if I remember correctly, 47, yes, 46 point some change, that means 47 ohms. And the last one is 100K, 99.4. So that means this is a 100K resistor. And we didn't have to change again ranges. When we want to measure anything, at first we select the desired range, but the first thing multimeter wants to measure is the white character marking. So in this case it wants to measure ohms. If we want to measure anything else, it can measure in this range, meaning diode testing or capacitance. We have to push once the blue button, meaning now it's manual selection, and we have to select, in this case we want to measure some capacitance, so we want to select not the continuity, not the diode testing, but the nanofarad. And let's measure some capacitances. The first one, it says on it 33 nanofarad. We measure only 29. The second one, if I remember correctly, was 150 nanofarad. Doesn't, yes, 151, pretty close. The third one, I think 1 micro, Let's see. Yes, almost 962 nanofarads, which means 1 microfarad. The next one is an electrolytic. It should be 10 microfarads. We measure 11.4. The next one is a 47 micro. Let's see. Yeah, 43 is pretty low. The next one is we don't know yet. 100 microfarad, almost bang on. Excellent. And the last one is 470, which measures pretty high, 516. So that's how we measure capacitances.
And this old multimeter is measured.
This one measures up to 20 microfarads only. This one measures easily 500 and some change. I don't know what is the highest. And this one doesn't measure capacitances. We constructed a little circuit with a simple circuit with an LED, a 9-volt battery, and of course, to limit the current, we put in series a resistor and a variable resistor, a potentiometer. The system works like this. We can limit less or more the current flowing through the LED. This is the less current, and if I adjust the potentiometer, this is the highest current. We bring it down for a moment. If we want to measure the current flowing through the circuit, we at first should select milliamps range, and of course we need to switch the probes so that we can measure amps. Now we of course break the circuit and we simply touch the probes to these two jumper wires. Now it displays 0.6 milliamps. If I ask my colleague to adjust the potentiometer with his right hand, should adjust it all the way to the left, the LED glows brighter and we observe that the multimeter displays 6.4 milliamps. We adjust it back, the current flowing through the circuit drops to 0.6.7 milliamps. Now we took out the 10K series resistor, we left in only the variable resistor, and we want to measure again the current with the same setup. Let's see what happens. Maybe the LED will blow up at some point. Now the current flowing is 0.6 milliamps. If we adjust it slightly to the left, now it's 1.6, now it's 2 point something, 11. LED brights up heavily and the current flowing is 162 milliamps, but I think the LED already is damaged. Yes, we managed to burn up the LED. Success.
The dead of the LED.
We are ready to measure some diodes. For that we select the third range and auto range it till we see the diode mode. But first we should check with our continuity tester these two diodes that we do know do not work anymore because we managed to blow them up. This one is shorted, obviously both ways. This other one is not shorted, seems to be open circuit, but if we select now the diode test mode, this one measures 0.9 of a volt, but it does both ways, which a diode should not do, because a diode conducts only in one direction. So these two are toast. Let's see how silicon diode, rectifier diode, behaves. We can see 0.6 of a volt drop across the diode, but that should be only in one direction. If I measure the other direction, it's OL, yeah? If we do that with an LED, probably the LED should light up during the test. Let's see. Yes, the red LED lit up, and we measure 1.6 of a volt voltage drop across it. Of course, this should happen only in one direction. If we reverse bias the LED, it measures an open circuit, yeah? The same with this one. The orange LED measures 1.8 of a volt drop across it, and does this only in one direction because it's a healthy LED. We can test BJT, bipolar junction transistor, for any shorts using again the diode test mode. BJT is or PNP or an NPN one. We don't know which one is this, so we randomly touch our test leads to, let's say, the first two terminals of our transistor, and immediately find a junction, a diode junction. We found out that this lead is a P and this lead is an N. We found our PN junction. Let's touch up our next lead, and we are extremely lucky because we immediately find our next PN junction. So this transistor is an NPN transistor. This lead is an N. The most left sided is a P, and the middle one is an N again. Of course, if we touch our junctions in reverse bias, the reading should be 0. Next, we want to measure some temperature. For that, we replace the normal test leads with this one, which has a polarity. Be aware of the negative and positive terminals. We switch on the multimeter on the second range, where we have millivolts, DC and AC, and temperature. We now see DC, so we want to select first manual, then press the yellow until the Celsius sign appears. Now the multimeter displays the ambient temperature, which is 22 degrees. Let's see what happens if we measure my beer. It reacts really slowly. Of course, this multimeter was not constructed to measure beer temperature. It probably reacts more if you try to measure a 100 degrees boiling transistor on something, or a heatsink. But we are patient to see how many degrees my beer is.
It's 11 degrees. We put a glass of water in the microwave.
We heated up some water to see how quick the multimeter reacts to hot water, but it's pretty quick, I would say. 90, almost boiling water. 95 degrees.
The water is not boiling, but the multimeter seems it's 100 degrees.
It's now stable at 99-98 degrees. Let's see how quick it returns to ambient temperature.
It's pretty quick.
Let's test our electromagnetic field measuring tool, NCV. In the wall we have our conductance slightly deeper, so it does not detect it anywhere. But there and at the switch it does. Some visual interpretation. If we want to measure mains voltage, then we should select voltage range, but the first thing we want to measure is DC, so we should press the blue button till manual appears, then one press at the yellow button should display AC. Then we can measure AC voltage easily. We have here his twin brother, the AN8008. This one was the 8009. There are a few differences. This one measures electromagnetic field This one doesn't, but it has a built-in square wave generator. So we now can test how this one measures hertz. For that we select the first position and switch on manual and press twice the yellow button until the hertz sign appears. Then we start up this other one, which generates 50 Hertz or 100 Hertz or whatever, and simply put our test leads into the banana plugs and immediately bang on 100 Hertz. If we select on the source something else, 200 Hertz, 300 immediately is measured with that multimeter. 400, let's see what it can do. 500, 6, 7, it's pretty quick. 1000 Hertz, that means a kilohertz, 2 kilohertz, 3, almost bang on, 5 kilohertz, 5 and 1, and 50 hertz again, and the cycle starts. It's pretty good. Of course, both of them have backlight. Long pressing the blue button, it lights up the screen. It is a nice feature. We are measuring now the same 9-volt battery with both of the multimeters, and the difference is negligible. Well, since I know you, and I know you are the one who is always against the system and always, practically you are the resistance, yeah? So let's measure your resistance value. 1.3 watt, 1.3 mega ohms, and rising. No.
Yes.
No, it's not. Make sure you have a good contact.
Very good contact.
Let's try your head or your brain. 70, 80, now it's rising. Yeah.
I am Einstein.
Your head is a problem.
I am Einstein.